is this 4s2 and the 3d4. The 3d4 is very unstable, meaning the D subshell contains 5 orbitals, right? I told you 1, 2, 3, 4 and 5. These are the 5 orbitals that we have. Remember, I told you that each orbital can have a maximum of how many electrons? 2 electrons only. Now, these are the 4 electrons. Now, meanwhile, I am discussing this, I'll also explain the Hund's rule. Hund's rule says that the electrons will always be added to the empty orbitals first, and then they'll get paired up. Okay? So these are the 4 electrons, right? The first electron, let's assume it's added to this orbital. The second electron will not come to this orbital because this has been partially filled. So the second electron will go on to the next orbital. Okay? Then the third and then the fourth. Empty seats will be filled first. According to Hund's rule, you are going to fill in the orbitals singly first. Excuse me. Now, these are the 4 electrons that we've accommodated. But remember guys, this is a very unstable configuration. Okay, this is an unstable configuration because this 4s2 over here, this 4s, what this 4s does is to become stable, this 4s, it causes one of its electrons to excite and partially fill the entire subshell. Okay, this 4s instead of the 2 becomes a 1 and the 3d instead of a 4 becomes a 5. Okay, because of stability. Whenever the d orbitals are half filled, they are very stable. And remember one thing, anything in nature would want to stay in its most stable form. Okay, stable means it's gonna exist in that form. Okay, its chance of existing increases. This is what stability means. It's not gonna change into some other substance. Okay, it's gonna stay as it is in this configuration. Whereas this configuration, which was the original one, according to the Opus principle, this was a less stable one. So anything in nature, any element would want to stay in the most stable form. So in order to achieve the maximum stability, this s electron is transferred to the next shell, the subshell, sorry. So this electron is excited to the d orbital. So 4s1 and 3d5 is the electronic configuration of chromium. Okay, instead of the expected 4s2 and 3d6 or 3d4. Okay, but this is the only exception. Chromium is one exception, and we also have a second exception to the Opus principle. It's copper. Its proton number is 29, right? It has 29 electrons. So let's add in the 29 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s and 3d. Now, in case of copper, according to the Opus principle, it should be 4s2 and 3d9. Okay, it should be, because if you count this up, it's gonna total up to 29. Okay, and according to Opus principle, the 4s needs to be filled first before we go on to the 3d orbital, right? According to Opus principle, because this arrow ends here and then the next arrow starts from here. But in this case only, the 3d9, if I were to draw in, okay, now let's assume that these 5 orbitals are for copper. Okay, and in the D subshell we've got a maximum of 10 electrons that we can accommodate, right? But we've got only 9 electrons over here in the 3D, right? The 9 electrons in this present state of copper, the 9 electrons, how are we going to fill in the 9 electrons according to Hund's rule? We're going to first fill in them singly, right? And then we are going to pair them up. So the 9 electrons, the first electron, second, third, fourth and fifth, we still left with 4 electrons. Now the pairing will start. Now the electrons have become paired. Okay, now these are 9 electrons. and whenever you are pairing them, so remember the electrons will have opposite directions, okay? They will have opposite spins, and this sign is for electrons, okay? It's not for data of your phones. It's not for data, okay? Remember, you guys recognize this sign? You can see it on your 4G, written next to the 4G on your data when you open the data, okay? Anyways, now these are the electrons that we have, the 9 electrons. Now this copper as well, in order to achieve maximum stability, what it does is, from its 4s orbital, which contains the 2 electrons, it causes one of the electron to go up. Basically it's 4s, right? So it's at a lower energy level. So what it does is, it causes one electron to jump up to the higher energy level, and as soon as this electron jumps up to the higher energy level, the d subshell completes. It completes itself, it becomes full. And remember, whenever a subshell is partially filled or fully filled, it's always in the most stable configuration. So this is also for stability, okay? So copper, instead of the 4s2, is actually 4s1 and 3d10. So it appears as if the 3d orbital is filled before the 4s. Actually, it's not filled, but rather it's for stability that the 4s is going to become 1 and the 3d is going to become 10. But what if we had, let's say, something with an atomic number of, let's say, 28. If we had an atomic number of 28, how are we going to write down the electronic configuration for this one? Now see, start out the same Aufbau's principle is going to apply. We'll start out from 1s2, 2 electrons gone, 26 left. 2s2, 2 more gone, 24 left. 2p6, 6 gone, so 20 left, right? Then 6, 8, 10 gone actually, so 18 left basically. After the 2p6 comes the 3s2, then the 3p6, then the 4s, and then the 3d, right? According to this principle. 1s, 2s, 2p, 3s, 3p, 4s, 3d. Now, we've filled in the 2s2, 1s2, 2s2, 2p6, 3s2, 3p6. So 6 plus 2 is, 6 plus 4 is 10, 2 is 12, plus 6 is 18. Now 18 electrons are gone. Out of the 28, we have added in 18 electrons. How many are we left? We are left with 10 electrons. Now out of the 10 electrons, we are going to fill in the 4s orbital first according to the Aufbau's principle, and then the 3d needs to be filled. Okay, so this is going to become the 4s2. How many are we left with? 8. So 3d 8. This is going to be the electronic configuration for an atomic number of 28. Okay, remember, just simply remember that you are going to follow this Aufbau's principle in every case except for these two, chromium and copper, because in chromium and copper it's the 4s that appears to be filled before the 3d. Okay, in all the other ones, see over here, because in copper and chromium it's a 3d that seems to be filled before the 4s, but over here in this case it's the 4s2 that is filled. The 4s is filled before the 3d. Okay, the 4s is 2 and it's completely filled, and the 3d is not completely filled. Okay, it's 3d 8, it's filled in the end, that's why. So this is how you're going to write down the electronic configuration. Clear? So that's completes in the electronic configuration. That's everything about the electronic configuration, and you can try out a few questions for yourself. Okay, let's try out this last thing about the Hund's rule. If we've got 5 electrons in the p orbital, how are we going to represent them in the orbital form? The 3 orbitals of pr, px, py and pz. Okay, 5 electrons are in here. So the first electron, then the second electron, will it be added to the same orbital? No, it will be added to the next one, because electron will always try to find an empty seat for himself. Okay, whenever you hop into a bus and you see that there are passengers already sitting in the bus, then you'll always try to go to the seat which is empty. Okay, you won't go try to get the half filled seat if there is an empty seat. So the electrons also have a similar behavior towards their seats. The seats are the orbitals in here. So first electron, then comes the second, then comes the third, then comes the fourth one. Now after the three are filled, the fourth one doesn't have a choice. It has to take one of the three half-filled seats, right? So it's gonna get added, and whenever it's added, its direction changes, okay? Because the electrons, basically we call this spin. The spin of the electron changes because of they are like charges, so in order to minimize repulsion, they change their direction of spin. Okay, and then the last one is this one. This is the Hund's rule. Okay, and I hope this clears everything about the Hund's rule, about the Aufbau's principle, and how you're going to write down the electronic configuration. Thank you.